Presentation basically is going to discuss wound rotor induction motor and our design fundamentals and the best practices for operation, installation, and application. We're going to discuss basically a little history with regards to the beginning of it. Wound rotor motors have been around for a long time, been used in many applications. Majority of history of the motors was after the initial design of the induction machine. There was a need for speed control, and the induction motor had some failures with regards to operating in speed control mode in its early stages. The wound rotor basically, in its history, indicated that it needed to have some framework in which you could operate the motor at varying speeds. The wound rotor configuration in the early 20th century and its practices basically appeared as a new design with regards to having and adding slip rings or external resistors to the motor. This innovation basically allowed engineers to overcome and short the squirrel cage portion of the rotor, particularly in heavy industry applications requiring high starting torque. In the 40s, basically, the expansion of wound rotor machines were adopted, and manufacturing of these were extensive, and they were used mostly in elevators, hoists, mills, conveyors, cranes, areas where some speed control was required, as well as high starting torque conditions. The benefit of a wound rotor machine is that you can have a large amount of torque with a minimal amount of inrush current. And then you do have some adjustability of speed between 50 and 100% in its current design. This increases the ability of the motor to operate. So basically you're generating a design D torque curve in starting, and then as you remove resistance on the rotor, then that drops out and takes you down to a design B operating condition. The motor provided some real benefits in that it had some smooth, controllable acceleration with regards to applications. The motor we have on the screen basically is Toshiba's design, and it can be manufactured in any enclosure that you require, from 150 to 1500 or 15,000 horsepower, and from 4 to 18 poles through with an IP55 capability. We can do horizontal and vertical, but our vertical is limited based upon the rotor weight. We can also provide it with either ball bearings or sleeve bearings, and the collector rings basically, because of the design, have a high degree of torque and current that will pass through that design. So our limitations with regards to some voltages, we can of course do low voltage as well as 3,000, 4160, 6,000, 6600, up to 11 kV. The collector ring design and the brush holding system that's part of the design are unique to Toshiba's design with regards to availability of operating conditions, as well as the benefits associated with keeping them clean. As you know, typically we see with brushes a fair amount of dust that's built up within the system. We have applied, in some cases, where we've installed additional blower assemblies to not only keep those units clear of dust and debris, but also it allows for a longer operating life. Go on to the next slide here. So the key features associated with it is that the wound rotor, much like a three-phase induction machine, has some real benefits with regards to its slip ring configuration. So an example is that when you're looking at a 4,500 horsepower wound rotor machine, 4, 6, or 8 pole design, you're passing a fair amount of current and voltage through those resistors. And you can see as much as 3,000 volts on a 4,500 horsepower machine. So the insulation characteristics associated with the rotor and the slip ring assemblies have to be able to manage both the temperature as well as the voltage conditions associated with those large machine rotor designs. The brush assemblies and brush holder assemblies can be either consistent, or they can have lifting ports on the rotor, allowing for the coil connections to be able to be lifted when you're at 100% of operating speed. The carbon brushes themselves make contact with those slip rings throughout the whole starting process, and then can be left in place for varying the speed, or can be lifted at the completion of operation. We see this typically where we're starting conveyor systems, and we see that the spring assembly and the associated rings and ring barriers can be maintained fairly easily and readily. The starting circuit, basically at full speed, the mechanism can be removed with regards to the resistance on the machine. So typically the resistors themselves, there's many different types. You can use contactor assemblies to bring the resistors in and out, or you can use a liquid basically starter that pumps liquid in and out of the three phases that make connection to the rotor. And that rotor assembly, when you look at it, has the barriers between each phase, as well as the unique slip ring designs, which are typically bronze or copper with regards to their design. They're not like a synchronous motor in its configuration, where you're looking at minimal voltages and currents, but are designed for more robust configuration and operation. So this just shows a single connection on the slip ring itself, but the design characteristics associated with the rotor and rotor assembly means it will handle very high difficult loads with a lot of kVA demand. And so you're looking at a winding that's internal to the rotor, three-phase, that is configured such that it handles high torque and high load characteristics. Again, going back to NEMA Design C for starting conditions. The rotor directly applies the voltage and current and through the resistors and the rotating circuit field. Why is the voltage rotor energized like it is? It allows it to be shorted out, and the resistor control will allow for variable speed. It's the law of electromagnetic induction. It causes the current to flow in the rotor winding and generating additional torque. Now we look at applications and say to ourselves, why would this be necessary? And if you're not requiring special conditions for long periods of time, this design with wound rotor machine can be very cost effective. Now it does require additional maintenance and additional equipment associated with it, but it's far less than using a variable frequency drive. When we look at the slip ring and gear assembly, the configuration typically looks something like this. We have a brush holder assembly, separate mounting plate as part of the front of the brush holder assembly. We have constant force spring assemblies and pigtails that come off those that make connections. And then the brushes themselves make contact against the surface of the commutator, and then separate barriers between each of the phases associated with the rotor. You have the insulation itself on the rotor that separates the shaft from the commutator assembly or slip rings, and then they're all bolted together basically to complete a formal shorted or non-shorted, rotating assembly. The slip rings basically help make good contact, and the ring itself oftentimes has grooves built into it that are machined that are identifying the wear points on the slip rings themselves. Basically, you're always looking at what those carbon brushes do for makeup and for quality and for longevity. We can supply additional carbon brushes to ensure that you have reliability with the machine for continuous operation. You do have a fair amount of dust that does build up in this system. Again, you would see regular maintenance of it, but the idea is that it has a need for the continuous cleaning. You know, you'd go in every 2 months or so, or once a quarter, and you'd actually go in and clean and make sure that the brush in facility, the enclosure basically is clean. I had a question just a second ago with regards to it. Let's see. Question was, is there special starting requirements? Besides using the resistors in the starting circuit, there aren't additional starting conditions that are required. We find a lot of people these days removing the connections on the resistor and tagging them out and wanting to use it as an induction machine. But what you lose in that process is the additional torque during the starting process. You can see as much as 250 to 300% starting torque with the resistors in place. And that goes away when you use it as an induction machine. This just shows the regular construction as a point with regards to the frame. This is a TAC machine, typical induction with regards to how it appears. You have your basically your frame, your shaft assembly. the end brackets, and then the top hat assembly, and the frame heaters, which would be with any machine. When we get into the differences, it is in the back end of the motor with regards to the extended shaft and shaft assembly, and the slip ring assemblies and the fan cover associated with it. The fan actually can act as a draw across it, and forcing air through the slip ring compartment. This is typical for the assembly process for a wound rotor machine. Coil assemblies, because you draw so much more current through the rotor and rotor assembly, we typically use higher insulating patterns and materials in the rotor and rotor assembly to deal with that excess temperature and the current that's drawn across them. And so that's part of the design characteristics. I want to just stop right here and just talk about some of the materials that makes us different. We're using C5 and C6 grade steel as part of the design. And that's simply because of, again, the initial temperature and temperature conditions during starting that is seen in a wound rotor design. We've had customers who say, well, it should be a lower cost with regards to operating conditions, and we don't see that as much as you would think with regards to the fact that it has a separate field assembly actually built into the rotor itself, three-phase. The end plates and offers rigidity, and so it's designed for severe duty, and the coil constructions that protect the motor offer thermal breakdown protection and is considered for heavy applications. And we'll get into the winding slot assembly here in a second, but it's basically banded on the ends to handle the forces and then welded across the surface of both the rotor and the stator to hold things in place. They use a mica tape as well as a VPI epoxy resin as part of the design when the completed motor is still Class F insulated, but usually has a higher insulating capability than the 150 degree temperature condition. It's typically 180, so it's Class H. But the leads actually eliminate that. So when we're looking at the design, the characteristics, again, are form wound coils. So you're looking at a 25-year service life, and the development basically that Toshiba used specific to the materials, again, provides a very high thermal rating. The provided voltage characteristics, again, through 15,000 volt capability with regards to the wound rotor machine. We recognize that these are often used in difficult applications, and so we're looking at the correct bracing and support needed for operating the motor under those conditions. So the resistor compartment, basically, or the commutation end of the motor, the slip ring sections, is separately attached. It's sitting in its own compartment and is typically rated for IP55 connection environment. So oftentimes we get asked if we can just apply a wound rotor machine. And since we know that it's a designed D starting condition, we can look at it and say that the resistor at any given point, because you can have series resistors in place during starting, that you can have many different starting conditions associated with it. And by simply bringing resistors in or out of the motor start condition. Low resistance rotors are better suited for low slip at high loads and high efficiency. And we know that with a wound rotor, it offers the best of both of those worlds. The differences basically show that the R1 starting circuit basically provides very high starting conditions, as we've talked about. So we can apply these in a various areas of the industry, including hoists and cranes, cement mills, ball mills, rolling mills, conveyors. We see a lot of applications in conveyors, elevators, usually material elevators, compressors with high starting torque requirements, with low current and basically a lower cost in some cases. Again, having some variable speed with regards to the latter part of the curve. And then, of course, Banbury mixers and large fans. Wound rotors used in all of these areas and have been for a long time. In general, basically, they offer stability in operation, and the benefits is that you have a lower installation cost. You do have higher degree of maintenance that's part of the process, but if that is known going in, then that can be accounted for. There are things called slip recovery drives that can be applied to wound rotor machine, in which the resistors are part of the circuit during the starting process, but as it's brought up to speed, the resistors are dropped out and the drive then becomes part of the control process. The T300 basically can be applied to this type of circuit. You can see here from the electrical diagram that the PWM output can be used for its control. It can then also be switched to the line as part of the design circuit. So you get the benefits of both the PWM starting circuit as well as the improved characteristics of control at a lower speed. Benefits is high starting torque and then variable speed output. But you do have all of the resistance plus the VFD in the circuit. So there is a higher upfront cost. Are there any questions? Okay, well, this was brief. If you have any questions, we look forward to hearing from you.
Ken, I think we have a few through the Q&A. You may have to turn it off and back on to update, but there are some.
Are there concerns with induced current impacting bearings with wound rotor motors? No, simply because we're not seeing an out-of-phase PWM condition that can cause bearing damage. You do have to take that in consideration with regards to temperature rise, but in most cases, the temperatures, the bearing designs, and the oil or grease is protected, will protect the bearings themselves. So we don't see that like you do with a VFD. Okay, next one. Does Toshiba still manufacture wound rotor motors, and in which factory do they come from? These are manufactured through Toshiba's production overseas. We have that capability. Houston's focus is API 541 design, copper bar design, rotors, and die-cast aluminum. But the rest of those can be manufactured through Toshiba sources that are overseas, or plants, I should say. Toshiba does build the starters with the resistors in place. The CASD group can help provide that. We also can provide a liquid rheostat as a design and apply that at the time that the motor is sold. The next question is can Toshiba manufacture wound rotor machines at 4160 and 460 volt? The answer is yes and yes. It just depends on what size you're looking at doing. We typically build larger machines, not necessarily, things below 150 horsepower. Okay, any other questions? All right. Thank you for listening to us today, and if you have any questions, we look forward to answering them.
And I think we've got a few more down. Maybe scroll down a little bit.
Okay.
Thank you.
2 new ones. Let's see. How long have they been manufacturing wound rotor motors? Since the 1930s. What is the current market for wound rotor machines? Has Houston built a T300? No, I can't answer the comments with regards to the VFD portion of it. I do know that the technology exists. Okay. And wound rotor typo. So, sorry, there was a typo in there somewhere. Any others? Are secondary resistor control systems the best solution for wound rotor induction machines? There are options available based on the current. So the larger the machine, at some point it becomes not cost effective to use resistors and contactors. At a given point where those when those systems basically come together, sometimes it's better to go to a liquid resistor package. Get a training video sent to you. There are we can certainly look at whatever you need with regards to training videos on wound rotor machines, but they vary based upon the requirements and the systems that are part of it. So you would provide to us a specification as to what you or your customer is requesting, and then we would go ahead and manufacture that and define exactly the materials that we would provide within the wound rotor machine. Control resistors are basically what is meant with regards to the output control of the rotor assembly, and that resistor package basically can be a series of resistors, and they can be steel, they can be enamel coated and wrapped wire that would provide to the resistance associated with starting the circuits. You can use soft starts, but not to generate the same level of torque that you can create with a wound rotor motor. A soft start, because it limits the input voltage, you're basically starving the motor of voltage, and you end up not having the same degree of torque generated. So if you have a conveyor, for example, and I've seen this personally, where a soft start was applied and it didn't generate sufficient torque to be able to get the conveyor started, where a wound rotor motor with the resistors could provide the higher starting torque conditions. Again, design D starting conditions, and then as the resistors are dropped out, it goes to a design B configuration. Robert writes, other benefits of using soft starts versus, and I think you're thinking of a wound rotor machine. The benefits of a VFD, of course, is that you can create up to the breakdown torque on an induction machine during starting condition. The benefit of a wound rotor machine is you can actually exceed that by changing the slip within the rotor and the stator, where the voltage and frequency is adjusting the output on a VFD to 60 hertz. So there are some benefits with regards to wound rotor machines, and that's why they're still being used, for example, in conveyors and in ball mills, is because you can actually benefit by changing that slip within the rotor.